Look closely at the world around you. The smooth arc of a falling leaf, the continuous flow of water in a quiet stream, the endless, uninterrupted void of the night sky. For the entire 13.8 billion years of our cosmic history, the universe has presented us with a beautifully convincing illusion. The illusion of perfect, uninterrupted smoothness. We naturally believe that space is a flawless, infinite canvas, an empty stage where the dramatic events of reality take place. But if you take a photograph of that beautiful galaxy and zoom in close enough, the smooth image suddenly vanishes. It breaks apart into a rigid, structured grid, a mosaic made of millions of tiny, indivisible squares. You reach the resolution limit. What if I told you that the universe operates on the exact same principle? That reality itself might actually be pixelated? That the space you move through every single day, even the seemingly empty distance between your hands, is not continuous at all. Instead, reality has a fundamental resolution limit, a microscopic flaw where the very concept of smaller simply ceases to exist. To understand this mind-bending concept, we have to talk about the greatest, messiest, and most frustrating divorce in the history of science. On one side, we have Albert Einstein and his absolute masterpiece, the elegant theory of general relativity, published in 1915. General relativity describes gravity not as a pulling force, but as the warping of a beautifully smooth, continuous space-time fabric. It perfectly predicts the majestic dance of galaxies, the orbits of planets, and the gentle bending of starlight around massive objects. But on the other side of the laboratory, we have quantum mechanics, the bizarre, unpredictable rulebook governing the microscopic world of atoms. And quantum mechanics fundamentally hates the idea of smoothness. In the quantum realm, everything is delivered in choppy, discrete, jittery packets. For decades, these two completely different mathematical rulebooks have worked flawlessly in their own isolated domains, never stepping on each other's toes. General relativity is the undisputed king of the macroscopic universe, gracefully governing the slow, elegant orbits of planets and the dance of galaxies. Meanwhile, quantum mechanics rules the microscopic realm. Niels Bohr and his colleagues showed it predicts the chaotic behavior of subatomic particles with astonishing precision. Most of the time, they never need to interact. A star is too massive to care about quantum jitter, and an atom ignores gravity. But there are extreme places in the cosmos where this peaceful separation is abruptly shattered, forcing the two worlds into a dramatic cosmic interaction. The most notorious battleground is the center of a black hole, a place where the delicate fabric of reality is stretched to its absolute breaking point. Imagine a dying star, containing the mass of several million suns, completely collapsing inward under the immense, crushing weight of its own gravity. Gravity pulls all that incredible mass inward, shrinking it down until it is smaller than a mountain, then smaller than a single grain of sand. Eventually, all that matter is compressed into a space smaller than a single atom. Physicists call this infinitely dense point a singularity. This is where the ultimate nightmare for physicists begins. Because a singularity is incredibly massive, we absolutely must use Einstein's equations of gravity. But because it is incredibly tiny, far smaller than an atom's diameter of 10 to the negative 10 meters, we must simultaneously use quantum mechanics. When you force these two opposing mathematical frameworks to work together on the exact same object, they absolutely refuse to cooperate with each other. The beautifully smooth geometric curves of relativity are completely distorted by the unpredictable, jittering static of the quantum foam. The math simply stops working. The equations produce infinite numbers and nonsensical errors. It is nature's way of putting up a giant stop sign, declaring that our theories are broken. This catastrophic failure at the center of a black hole tells us one profound truth. We are missing a fundamental piece of the cosmic puzzle. To fix this catastrophic failure of physics, we must ask a seemingly simple question. What happens if we just keep zooming in on empty space? If you cut a piece of paper in half, and then in half again, could you do it forever? Or would you eventually hit a wall? In 1899, the physicist Max Planck gave us the answer. He calculated the absolute fundamental flaw of reality, known today as the Planck length. How incredibly small is it? Imagine taking a single, microscopic atom and magically expanding it until it is the size of the entire observable universe. On that ridiculous cosmic scale, the Planck length would be roughly the size of a standard, everyday tree. It is 10 to the negative 35 meters. At this unimaginably tiny scale, the smooth, predictable rules of geometry that Einstein relied upon completely collapse into a chaotic, boiling mess. The legendary physicist John Wheeler famously named this the quantum foam. Here, space and time are no longer continuous. They constantly bubble and jitter. Virtual particles pop into existence and vanish instantly. Space itself contorts into microscopic wormholes, gracefully warping and stitching itself back together in a fraction of a second. The time it takes for light to cross this tiny distance is called the Planck time, 10 to the negative 43 seconds. The absolute shortest tick of the cosmic clock. Below this limit, the concepts of left, right, before, and after lose all physical meaning. It is the absolute pixel size of our universe. But what actually happens if you try to build a hypothetical microscope powerful enough to see something even smaller than this ultimate cosmic limit? To see smaller things, physicists must use particles with higher energy. The smaller the object you want to look at, the more concentrated energy you need. To observe something smaller than the Planck length, your hypothetical microscope would have to concentrate an absurd amount of energy into an infinitesimally small point. According to Einstein, mass and energy are interchangeable. So packing that much energy into a single microscopic point creates an immense gravitational pull. The very act of looking would cause that tiny region of space to collapse in on itself, creating a microscopic black hole that absorbs the light, hiding the secret forever. If we cannot zoom in infinitely, and space has a fundamental limit, we are left with a massive question. What exactly is space made of? In the late 1980s, a group of physicists decided to rethink the very foundation of reality, stepping away from popular, complex ideas like string theory. Enter Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, the pioneers of a radical new scientific hypothesis known as loop quantum gravity. To understand their theory, we must discard our most basic assumption. We usually think of space as a giant empty container, a theatrical stage where matter moves. But loop quantum gravity suggests that space is not the stage. There is no container. Space is the physical material itself. Imagine a beautiful, intricate piece of chainmail armor. From far away, it looks like a smooth, continuous, solid piece of fabric. But up close, you see it is entirely constructed of individual, interconnected metal rings. According to this theory, the universe is built the exact same way. In this framework, the smooth fabric of space-time is actually woven together by finite, indivisible loops. They are the quanta of space. Each one of these tiny loops holds an unimaginably small volume, roughly 10 to the negative 99 cubic centimeters. You literally cannot have a volume smaller than this. Now, looking at this mesh, your brain will naturally ask a very logical question. What exists in the empty gaps between these loops? The answer is absolutely nothing. There is no between, because these loops literally are space. The concept of distance outside of them simply does not exist. You are not moving through space. You are hopping discretely from one loop of the cosmic mesh to another, exactly like a character moving across pixels on a screen. And in this radical view, even time is an illusion. Time is simply the sequence of these fundamental loops, changing and interacting with each other. So when massive objects like stars exist in this network, they don't bend a smooth fabric. Instead, they pull and distort the density of these woven loops, creating gravity. And this granular, woven nature of reality finally gives us a way to survive the crushing center of a black hole without the mathematics exploding into nonsense. Let us journey back into the heart of darkness. Under Einstein's classical relativity, the matter inside a black hole collapses into an infinitely dense singularity. A singularity is a point of zero volume and infinite gravity. But in physics, Infinity usually just means your mathematical equations have completely failed. Loop quantum gravity changes the rules of the game entirely. Because space is made of finite, indivisible woven loops, it cannot be compressed infinitely. Think of the cosmic loops as microscopic, unbreakable building blocks. You can pack them incredibly tightly together, but you cannot squeeze them into nothingness. Imagine trying to compress a handful of solid wooden blocks in your hands. No matter how hard you push, they will eventually push back. In loop quantum gravity, this exact phenomenon occurs at the Planck scale. Physicists cleverly call this powerful fundamental counterforce quantum pressure or quantum repulsion. When a massive star collapses, gravity compresses the matter inward, breaking down atoms and quarks, forcing them into the smallest possible pockets of space. But right before it reaches absolute zero volume, the fundamental loops of space-time itself rebel. They physically refuse to be compressed any further. In 2014, physicists Carlo Rovelli and Francesca Vidotto hypothesized that the collapsing matter halts, forming a microscopic core known as a Planck star. This theoretical object is astonishingly tiny, often smaller than a single proton, but it safely holds the compressed mass of an entire heavy star. To understand this density, a neutron star packs a mountain into a teaspoon. A Planck star packs multiple suns into a single atomic space. Mathematically, it reaches the absolute limit of nature, the Planck density. That is, 10 to the power of 93 grams per cubic centimeter. The terrifying infinite singularity is officially erased from the math. But a Planck star doesn't just sit there peacefully. The immense quantum pressure is restless. Like a tightly coiled metal spring or a deeply squeezed rubber ball, the ultimate laws of quantum mechanics dictate that it must eventually rebound. The Planck star experiences a rapid quantum bounce, gently pushing the matter back outward. And this microscopic rebound has staggering implications for our origins. If a microscopic black hole bounces back because space cannot be infinitely crushed, what does this mean for the greatest singularity of all? Let us rewind the cosmic clock. If we run time backward for 13.8 billion years, the entire observable universe shrinks. Under classical physics, all matter and energy crush down into a single point of zero volume and infinite density. The infamous Big Bang singularity. But as we have just learned inside the black hole, infinity is merely nature's way of saying our mathematical models are fundamentally broken. In the early 2000s, physicist Abhay Ashtekar and his colleagues took a bold step, applying the rules of loop quantum gravity to the entire cosmos. This birthed a new field, loop quantum cosmology. They realized that the universe itself is constructed from those exact same finite, indivisible woven loops. Therefore, the early universe could not have started from a point of zero volume. Space simply refuses to be compressed into absolute nothingness. Instead, imagine a previous ancient universe collapsing inward under its own immense gravity, shrinking down until it reaches the absolute microscopic limit of the spin network. When it hits that fundamental Planck scale floor, the immense quantum pressure builds up, violently resisting any further compression. The cosmic spring is wound to its maximum. The ultimate result is not an explosion out of nothingness, but a magnificent quantum rebound. Physicists call this breathtaking event the Big Bounce. Our universe did not begin from a catastrophic dead end. It bounced back from the graceful, inevitable collapse of a previous cosmic era. This breathtaking mathematical hypothesis suggests a cyclical cosmos, an eternal chain of universes expanding, collapsing, and rebounding like a slowly beating cosmic heart. But this raises a fascinating, undeniable question. If we are just the latest breath in a cosmic cycle, can we actually see the previous universe? Scientists are actively searching the cosmic microwave background, the oldest light we can observe, for faint circular scars or gravitational ripples left over from the Great Bounce. While we wait for concrete proof of these ancient echoes, physicists must figure out how to test this pixelated reality here and now in our present universe. To prove that space is actually made of pixels, physicists came up with a brilliant idea involving light. Normally, all light travels at the exact same speed. But if space is a bumpy, woven mesh, higher energy light might interact with the tiny loops more than lower energy light, causing a microscopic delay. The problem? This delay is so unbelievably small that if you measured light traveling from the Sun to Earth, you would never ever notice it. To actually see the effect of this pixelated space, you need the light to travel across the entire universe, magnifying the tiny delay over billions of years. Enter gamma-ray bursts. These are the most energetic explosions in the cosmos, firing intense beams of light across billions of light-years of space. By the time those photons reach our telescopes, after traveling for 7 billion years, the high-energy light should arrive just a fraction of a second later than the rest. In recent years, satellites like the Fermi Space Telescope have carefully measured these ancient gamma-ray bursts, looking for that exact tiny delay. The results? So far, they have found absolutely nothing. The high-energy and low-energy photons seem to arrive at the exact same time. Does this mean loop quantum gravity is wrong? Not necessarily. The pixels of space might simply be arranged in a way that doesn't slow down the light. The search for the fundamental flaw of reality continues. Whether it is woven loops, vibrating strings, or something we haven't even imagined yet. But this journey down to the Planck scale leaves us with a profoundly beautiful realization about our place in the cosmos. Every single thing you touch, every step you take, and the very space that separates you from the stars might just be an illusion of smoothness. We are not simply living in the universe. We are riding on a breathtaking, microscopic mosaic, a pixelated masterpiece that holds reality itself together. If you enjoyed this journey into the quantum realm, consider subscribing. There is always more of the cosmos to explore. Thank you so much for watching, and as always, keep looking up.